All right, so in this video, we're going to look at counting rules that we can use, particularly for counting the number of things that will occur and also calculating probabilities in complex situations. So the main three things that we're going to look at, the main three scenarios are with repetition where order matters, and this is going to be the fundamental counting principle. We're going to be looking at no repetition where order matters, which is a permutation scenario, and then also without repetition and where order doesn't matter, which is the combination scenario. Now, there are other counting situations, and particularly a fourth scenario where repetition is allowed, but order doesn't matter, as in counting the number of ways that you can choose a dozen donuts, for instance, when you can choose multiple versions of the same donut, but you don't care what order you take those donuts in. That I will leave aside for now, but we don't usually use that a lot in probability calculations. We do use these three methods much more frequently. So those are the ones we're going to focus on. So to begin with the fundamental counting principle, this is basically the most basic rule of counting. All of the other methods are essentially derived from this basic notion in some idea. So we're going to start with a two-digit number example. So we have digit 1 and digit 2. And so one possible method of counting the number of two-digit numbers would be to make a list of all of them and then count them. But as the number of options grows beyond a handful or maybe two handfuls, you don't really want to do that. Listing all the possible outcomes is tedious, and again, sometimes like when you're doing license plates with 6 digits, you don't really want to list all the possibilities. That's crazy. So we want to calculate the number of them without keeping track of exactly what the individual possibilities are. Because for calculating probabilities, we don't actually care about the individual outcomes. We just care about the accumulated number of them. Now, if we're trying to calculate a two-digit number, then how many numbers can we specify in each spot? Now, if we force 0 to be a possible initial value, then we would have 10 total digits in digit 1. But in some systems, you can't specify 1 as a two-digit number. And in that case, you're not allowed to have the 0 as the first digit, in which case we would have only 9 possibilities for digit 1. But then in our second digit, we can use 0 because that doesn't reduce the number of digits. And so we would then have 10 possibilities for digit 2. And then that would give us two-digit numbers. There would be 90 of them. Now, there would be 100 of them, as I said, if you were able to specify 0, 1, and not just 1. The context of the problem is going to determine whether you're allowed to have 0 as the first digit or not. Now, suppose we wish to determine the number of three-letter words whose middle letter is a vowel and whose first and last letters were consonants. So we have a three-letter word, and so we're going to divide this up into basically 3 bins. We're going to figure out how many we can put in each of the bins and then multiply them. So the vowels in English are A, E, I, O, and U. So there are 5 vowels. So that goes in letter number 2 since the middle letter is a vowel. Now, we do have some words in English that count Y as a vowel. However, for this type of problem, you generally should consider Y a consonant because that's what it does most of the time. It's technically sort of halfway in between, but we want to be able to eliminate things like Y. So no overlaps. And then therefore the consonants in the first 2 letters would be the remaining number of letters in the English alphabet. So there are 26 total letters. If 5 of them are vowels, that leaves us with 21 consonants. And therefore 21 would go in the first space and 21 would go in the third space. And then we would multiply these together to get the total number of options. So 21 times 5 times 21 turns out to be 2205. So a similar example would be how many possible telephone numbers are there for each telephone exchange? So within each area code, essentially. Within each area code, there are exchanges that used to count for like towns or localities. So if we pick a particular exchange, like 555, which is basically just for television shows, the first digit would be specified, the second digit would be specified, and the third digit would be specified. And then the 4 remaining digits of your telephone number would be free to be any possible value. So they would have 10 outcomes each. And so then we would multiply those together to get 10,000 in this case. Now, if we were talking about telephone numbers within an area code, then these values here would not be ones, they would be something else. And we would have to think about the rules for these extensions. So typically for these telephone exchanges, they don't start with 0 or 1. And there may be other rules that you would have to worry about, but at the least, they can't start with 0 or 1 because that will either take you to the operator if you just start dialing, or they will think it's a long distance number. These other 2 digits are more free, but then you would have, within an area code, you would have more options because you would have more digits that are freely available. This is just 10,000 numbers, again, with an individual exchange. Many years ago, they broke up many area codes because they were running out of telephone numbers within the area code that they could use. Another example, we could think of alphanumeric passcodes. So alphanumeric passcodes mean that you can use any number or letter. So there are 26 letters and 10 numbers. Alphanumeric would then be 36 possible options in each digit. And if we aren't allowed to use special characters, which are these days typically mandatory, but let's assume you're only allowed to use alphanumeric characters, then there would be 36 possibilities for each position. And then in theory, you would have 36 to the 6th power, since this is a 6-digit password, 6-letter password, 6-character password, whatever you want to call it. And when you multiply this out, you end up with 2,176,782,336 possible combinations of passwords. And when you add special characters, of course, then the number of options goes way, way up. Now, always when you're solving these problems, read the problem through very carefully. You want to find the question in the problem. That will tell you exactly what you're looking for. You want to find out how many parts you can divide the problem into. So sometimes the problem will be explicit, like examples A and C, where we had 3-digit word or a 6-letter password. Sometimes the problem will be less explicit and ask you to know something about the world that's common. So example 2, we needed to know what telephone numbers were, that there's 7 digits and the first 3 digits are the exchange. But you can do similar problems with a fixed area code. You would then have the first 3 digits out of 10 be the area code, and then this remaining 7 digits would be the telephone number inside that area code. You would still need to take into account the fact that the exchanges don't start with 0 or 1. You may want to look for any restrictions on any of the digits. For example, in 2, we wanted to know only about the exchange or a single exchange. So that fixed the first 3 digits of the number to a single possibility. In example 1, we restricted the middle letter to just vowels and the outside letters to just consonants. So we weren't using all of the letters in each position. You can use this method also for permutation problems, which we're going to see a little bit later. But you also want to check to make sure that repetition is allowed. Permutation problems do not allow repetition, and so you would have to modify the problem, the way that you set this up, if repetition is not allowed. So are you allowed to use the same digit or letter twice? So for instance, is in number 3, in our third example, is BIB allowed? There's nothing in the problem that says that it's not, and therefore it's fine. But check out, we're going to talk about permutations next. And so usually they will have to specify, or there will be a context in which it's clear that you're not allowed to repeat. But that may be something that you have to ask as you go through these problems. You might want to look for any possible ambiguities and attempt to resolve these logically. Again, these may require information about the real world in order to understand exactly what you need to do. That will help disambiguate. And also you want to look for commonalities between problems. You will often find that passwords will use the fundamental counting principle, but card games will use another method that we'll come to below. Now let's go on to permutations. Now permutations and combinations are going to need to introduce a new mathematical notation, which is this exclamation point, which we use for constructing factorials. And 8 factorial is essentially defined as 8 times every number below it up down to 1. So 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So this table of factorials gives us a flavor of the sequence. So 0 factorial is defined to be 1. 1 factorial is 1. And then the pattern continues. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1, which is 6. 4 factorial is 4 times 3 times 2 times 1, which is 24, and so on. 5 factorial is 120. 6 factorial is 720. 7 factorial is 5040, and so forth. Now, in your TI calculator, you can find the factorial key under the math menu. Scroll over to the probability submenu, and then you'll see here it is the 4th option in the list. Now, permutations involve all possible arrangements of a set of numbers where order matters with no repetition. So here we're going to look at the set of the numbers 5, 6, 7, and 8. And we want to reorganize these in every possible conceivable way that is unique. So all the possible permutations of these numbers are listed here. So 5, 6, 7, 8, 5, 6, 8, 7, 5, 8, 6, 7, 5, 8, 7, 6, etc., etc., etc. And what we want to do is we want to find the number of these objects that are possible. It turns out there's 24 of them if you list all the possible ways. And as you increase the number of elements in your set, then the number of permutations increases dramatically. If we have 6 elements in our set and not 4, we end up with 720 possible permutations. Now, if we want to select fewer elements than are present, we might choose 2 elements of the 4 that were available, in which case we're looking at this list. Now, in this case, there are 12 permutations that are possible. And how would we go about calculating that? So the formula, sometimes you'll see the notation P of NR for permutations. N is the number of things you're choosing from. R is the number of things you're choosing. In the calculator, they use this notation NPR, but it's the same thing. N is the number of things you are choosing from. R is the number of things you are choosing. Sometimes they'll say picking to help distinguish permutations from combinations, but basically it's the same idea. And the formula is this: it's n factorial divided by n minus r factorial. So in this example, 4 factorial for our example of 5, 6, 7, 8, that's 4 things. So 4 factorial up top. For this list down here, we're choosing only 2 of them. So 4 minus 2 would be 2 factorial, we multiply these out, we end up with 24 over 2, which gets us 12. If we are choosing all of the things, as we saw in the original example, then our denominator becomes 4 minus 4. And remember, 0 factorial is 1. So this is just 4 factorial, which is 4 times 3 times 2 times 1, which is the 24 that we had in our list. So here we want to know what the number of possible permutations of a set of 10 elements are if we're using all 10 of them. So that would essentially be 10 factorial, which is 3,628,800. Again, anytime you're choosing all of the elements in your list and ordering them, it's basically just a factorial. The permutations formula is really only essential when you are not choosing all of the things in the list. So for example, how many possible permutations are there of 2 elements from a list of 3 elements, such as A, B, C? So we would calculate using our factorial formula, 3 factorial, 3 minus 2 factorial, we get 1 factorial in the denominator, and so we're just left with 3 factorial in this case. Again, since we're multiplying by 1 at the end, that last digit is forced to be a particular thing once you've chosen all the other ones. So you will also get n factorial when the denominator, when you only leave one thing out. How many possible permutations are there for 4 elements from a set of 10 elements, such as, again, the numbers, the digits 0 through 9? So here n is 10 and r is 3. And again, keep in mind, you can use this permutations formula that's in the calculator by typing in 10, then going to math, then the probability menu and selecting NPR from the table, which the same place where the factorial key is, and then typing in 3, and it will do all this math for you. But using the formula, 10 factorial divided by 7 factorial, all these things cancel out except for 10, 9, and 8. So start with 10, count down 3 elements, multiply them, you get 720. Now, some problem solving tips. Does order matter? If you answered yes, permutations might work, or you might need the fundamental counting principle. Is repetition allowed? If you answered yes, then you can't use permutations. That would be a fundamental counting principle. Sometimes your problem will say explicitly, but usually it won't. If you are choosing balls in a large state lottery, each number can only be chosen once, and you win more if you get the order correct as well. So permutations might be appropriate. Whenever you are ordering people, since people can't be in 2 places at once, permutations are appropriate if the order matters. For instance, if you are assigning officers or first, second, and third places, for instance, if you're unsure, you might put yourself into the problem. Would you care if you were chosen first or second? If the answer is yes, then use permutations. Do you have a number of objects with the same label, like blue balls or something? Then order is not really relevant because you can't tell those blue balls apart. So you have a different kind of problem. And then again, for using this in the calculator, if we wanted to calculate 7 pick 4, or using the permutations formula, 7 objects, we're choosing 4 of them and order matters. So then we would type 7, we would go to the math button, scroll over to the probability menu. The second option on the list would be NPR, and then we would type 4. And then when you hit enter, it will do all of those factorial calculations and canceling for you and get 840. And then the last counting rule we're going to look at are combinations. So combinations are somewhat similar to the permutations, except that order doesn't matter. So if we were choosing all of these items, then we don't care what order they're in, and all those reorderings that we were listing in the permutations case wouldn't matter. And so we just have, if we're choosing all 4 of them, just this one thing. But if we choose fewer number of the maximum elements, then we do get several choices. So if we take only 2 of them, and again, if order doesn't matter, then we have 6 possible outcomes. Now, you can have notations for combinations that are similar to the ones for permutations, but changing C out for P. So C of NR would be a combinations formula. The calculator will list NCR, which is also common, where C again stands for combinations rather than permutations. But this is such a common notation that it actually has a special format that looks like this. When you see this, it's not a fraction or anything like that. It is a combinations calculation. They're telling you NCR, N choose R, 4 choose 2, for example. It is a combinations formula. Now, the exact way that combinations are calculated is with this combinations formula. It is similar to the permutations. The n factorial is the same. The n minus r factorial is the same. What is different is the r factorial in the denominator. That is going to make the number of possible outcomes smaller because you have more things in the denominator. That's, again, essentially taking away the sequence, the ordering process. So here, 4 choose 4, we would have 4 factorial. 4 minus 4 factorial would give us 0 factorial, which is 1. And then 4 factorial would cancel out the 4 factorial on top. And so we'd get 1. On the other hand, 4 choose 2, 4 minus, this would actually be 2, that's a typo. 4 minus 2 would be 2 factorial. We have another 2 factorial. And so our previous answer of 12 would be divided by 2 again, and we would get 6, which would take out the sequence of flipping those values into a different order. Combinations also appears in this idea known as Pascal's triangle. And so row 0 of Pascal's triangle would be a 1. And then row 1 would be a 1 and a 1. And all of the first entries in the rows are 1s all the way down. But then the middle entries are the sum of the 2 entries diagonal to it on the previous line. So this 2 would be the result of 1 plus 1, and this 3 would be the result of 1 plus 2, and this 3 would also be the result of 1 plus 1, 2 plus 1, and then this 4 would be the result of 1 plus 3, and this 4 would be the result of 3 plus 1, but this 6 would be the result of 3 plus 3, and so on. 10 would be 4 plus 6, and 20 would be 10 plus 10, and so on and so forth. And from here, you can tell the value. You would start with C choose 0, C choose 1. So this would be row 6, would be 6 choose 0, would be 1. 6 choose 6 would be, 6 choose 1 would be 6. 6 choose 2 would be 15. 6 choose 3 would be 20. 6 choose 4 would be 15 again. 6 choose 5 would be 6. And then 6 choose 6 would be 1 again. So some examples, how many dance couples can be formed from a group of 11 people? So here we're choosing from a set of 11, but couples are only 2 at a time. So this is 11 choose 2. And again, this is assuming that we're not worrying about like gender or anything like that. If we want to evaluate this notation, this is 5 choose 3. So we would have 5 factorial, 3 factorial, 5 minus 3 factorial. We would get 10 when we did all of the cancellation. One of the places where combinations shows up, you'll see sometimes in binomial probabilities where you're trying to expand a binomial term like this to a large power. Or you will also see it sometimes in like binomial probability calculations. In the binomial expansion formula, every component is going to have this form, n choose r, a to the n minus r, b to the r. So when you multiply this out, remember you're foiling a plus b times a plus b times a plus b times a plus b. And so the initial term of the sequence is 4 choose 0, a to the fourth, b to the 0, which is just 4 choose 0 is 1. And again, we could go back and see this from Pascal's triangle right here. This is our 4 choose something. 4 choose 0 is 1. And then r is 0, and then 4 minus 0 is 4. So that just leaves us with 1 times a to the fourth, or a to the fourth. The second term would be 4 choose 1, a cubed times b, and that would be a 4, a cubed b. 4 choose 2 would be a 6. Again, we can look at our Pascal's triangle to see that, a squared, b squared. 4 choose 3 is back to 4. This would be a b cubed, and then 4 choose 4 would be no a, is the a to the 0, and then just b to the fourth. And then when we put them all together, this would be our formula for that expansion. So some problem solving tips. Does the problem say specifically whether no repetition is allowed or that order doesn't matter? If the problem is not explicit, combination problems are used when order or ranking is impossible or not of any value. So consider people in a couple or a group. It doesn't matter who gets picked for the couple first. People who are finalists in a contest, if they don't all have the same status, then order matters. If they all get the same prize, order doesn't matter. Problems with multiple objects with the same label, like blue balls and green balls, order doesn't matter because you can't tell them apart. And also card games, doesn't matter whether you get a card in a full house first, last, or whatever. It doesn't, as long as you get the card in the end. For problems with people in it, again, try to put yourself in the problem to see if you care whether you are picked first or second. If you don't care, use combinations. And then, as I said, binomial probability and binomial expansion problems both use this combinations formula for those coefficients. All right,